Hi everyone, my name is Swati and I'm going to be talking about a faster interior point method for semi-definite programs. This is joint work with Haotian Jiang, Tarun Katuria, Yingtat Li, and Zhao Song. So I'll start with defining what an SDP is. You're given as input a cost matrix C and constraint matrices A1 through AM and a constraint vector B. And the goal is to find a positive semi-definite matrix X that satisfies these M equalities and also maximizes this objective. This bullet symbol here indicates the trace of C times X. So it's the inner product between two matrices. So as you can see, semi-definite programs are also convex programs because you're optimizing a linear objective over a convex set. And in fact, they are more than just a convex program. They unify linear programs as well as provide very strong relaxations for quadratically constrained quadratic programs. And because of this property, they arise naturally in a lot of different applications. So here's a very partial list of pretty famous results where they appear. In combinatorial optimization, SDPs have been useful in getting some of the best approximation ratios for very fundamental NP-hard problems, such as the ones listed here. But also in continuous optimization, in control theory and machine learning, they are useful for relaxations of non-convex programs, such as in matrix rank minimization and sum of squares stuff. So SDPs are quite important, and therefore it's also important to solve them fast. And that's the problem that we consider in this project. So given a general SDP of this form, our goal is to solve it to epsilon accuracy, where epsilon can be very small, so exponentially small. And when I say solve it to epsilon accuracy, it means we want to find a feasible X such that its objective is no more than epsilon additive worse than the true optimum value. Okay. Now, why do we care? Oh, sorry. Oh, yeah. I forgot that there are no interruptions. So why do we care about this very small epsilon setting? So in this setting, you have two different kinds of algorithms that help you achieve this goal. One is this cutting plane method kind of algorithm. And the way it works is it starts with a convex set that is guaranteed to contain the optimum. And in each iteration, you query an oracle and you cut the convex set by a constant factor, and you slowly zero in on the optimum. In contrast, interior point methods work in a slightly different way. Suppose you want to minimize this function f subject to some constraints. You encode those constraints in the form of this barrier function and have this scaling factor that shifts the emphasis between solving the problem f and, minimizing the problem f and actually staying inside your constraint set. So the difference between these two methods is quite big. In the cutting plane method, in each step, all you know is that your optimum is within some convex set. Whereas in interior point method, in each step, you know that the optimum solves this very specific set of optimality conditions. And so due to the more information that you have in the interior point setting, you would expect that it's faster for any given problem, faster than cutting plane method. But it turns out that prior to our work, for the case of semi-definite programs, this wasn't the case. The theoretical runtime of the fastest cutting plane method was better than that of the fastest interior point method. So our motivation for this whole project was to try to resolve this paradox. And in this paper, we achieved this goal. So I'll just give a bit of a setup of how interior point method works and what's the change that we made, and a very high level idea of what was our analysis technique. So this is your general SDP, as I mentioned. The first step is to write down the dual problem because that reduces the variable size from n square, which was the matrix size, to m, which is the number of constraints. And then you add this barrier function that encodes that the slack matrix is PSD. And these are just standard tricks in from optimization theory. And once you've got this modified dual SDP, the way standard interior point method works is you start with setting this scaling factor eta to be a very small number, like 0, and you find this and you minimize the problem. And then you increase eta a little bit and solve the resulting optimization problem using Newton method. So there's a trade-off between how much you can increase eta, because you want to increase it a lot so that you make progress, but you can't increase it too much because Newton method converges only when you're already close enough to the optimum. So this is how this is what it looks like. You start from the interior and you converge to the optimum. So when you apply this paradigm to our specific objective, which was this eta times this linear term plus negative log det, this is what the algorithm looks like. This is the standard algorithm. So this is the update for eta, and this is our Newton step. Now note that the Newton step uses the Hessian and the gradient. So the Hessian and the gradient computations for our objective are here, which come from directional derivatives of the negative log det. Again, a standard calculation. So the most expensive step per iteration can be seen to be this Hessian computation, because you have to do this trace of S inverse times a matrix and S inverse times another matrix. And so our algorithm was as follows. Instead of using the exact slack matrix to do that Hessian computation, we maintain an approximate slack matrix. Let's call it S tilde, which satisfies the property that it's close enough to the true slack. So you can use it for the computations and prove that things are still correct. But additionally, in order for these computations to be cheap, S tilde also, we show that S tilde also satisfies the following property. We show that over all the iterations of the algorithm, the total rank change in S tilde is bounded. And specifically, it's bounded by the following inequality. So if you go back to this line, what it's saying is that instead of using the true slack matrix, we use this S tilde, which is close enough to the true slack, but also doesn't change too much across the iterations, which means the updates in this approximate Hessian are not too crazy, and therefore they can be done cheaply. So in addition to this rank lemma, we also prove some properties of fast rectangular matrix multiplication. And combining these two technical lemmas that we prove, we are able to get a final result that our runtime for the interior point method is this expression here. And you can actually explain each of the terms in a very clear way. And if you just look at the table of past work, this was the previous best, the second from last row was the previous best cutting plane method. And I would like to draw your emphasis to the last two columns. So there, yeah, so you can see that we beat the previous best cutting plane result, which was our goal. And so there's always a question like, can you do this better? Can you get a faster runtime? And as of now, we don't see a way to improve this runtime, at least using our technique, because there are so many operations that we need to do that have these bottlenecks to improving the runtime. So right now we have a lot of dead ends to further improving this runtime. So maybe some other technique might work. That's all I had to say. Thank you for your attention.
Thank you. Let's thank the speaker. And now I guess we take questions over, like we have a few more minutes until the next talk. So if you have any questions, we can take them now. And I don't know if you guys want to raise your hands or just go ahead and ask them. I'm really not sure how to do this. So
I can ask a question if Marius is asking. Okay, I just want to understand what properties of this slack matrix S are you using to kind of build these approximations and keep them low rank throughout. So it seems like you compute the approximation fresh at every step. You compute the slack matrix and then compute S tilde.
Yes.
But presumably you are using the fact that this slack matrices S kind of vary slowly throughout the process so that you can keep updating your low rank bound on the new S tildes obtained at every step. Or how are you making sure that the rank bound is on somehow the trajectory of S tildes, where they are also being computed fresh at every step.
So we actually cannot prove that S itself has S doesn't change too much.
Okay.
Because in fact, if we could, that was something we tried, and if that had worked out, then you could have directly shown that H also changes very little just by this, because of this form. But the way we show that S tilde changes very little is through the use of this potential function that kind of measures, not really the difference, but like almost like a function which is kind of like a difference between, like a normalized difference between S and S tilde. And yeah, you look at its eigen decomposition and basically get rid of the large differences. So, and that's how you construct this new S tilde. Yeah, and through the use of this potential function, we are able to show that's a function of this matrix. You're able to show that that S tilde doesn't change that much.
And how generic is the transformation of going from S to S tilde? Do you need any properties of S to do that, or this is something for all matrices that you can define?
Yeah, you just need it to be PSD, which it is, and yeah, that's it. You just need it to be PSD. Yeah, and this was actually like this potential is actually inspired from the paper solving linear programs in matrix multiplication time by Cohen, Lee, and Song. They have a very similar, I mean, ours is similar to theirs. So their potential is, it's the instance of a slack inverse. They have this diagonal matrix. So it's also inverted, but it's element-wise inverse. And there they show that the L2 difference is not, L2 change is not too much. So in the matrix setting, that translates to the rank change not being too much.
Any more questions?
Yeah, I would have another question. So you solve it by looking at the dual formulation. Is that strictly better than solving it directly over the primal, or are there, if the relation between M and N is kind of fortunate, then that would be possible that if you go directly over the primal, that this would be faster?
I just think that if you try to do it over the primal space, okay, so like, because you're doing it in the dual space, your variable is an m-dimensional vector. So your gradient is an m-dimensional vector and your Hessian is an m by m matrix. But if you do it using the primal, your variables is this n by n matrix. So then your Hessian is just going to be a bit crazy, right? So I think.
Okay. So in the best case scenario, the primal is only as good as the dual, but in the worst case, the dual is infinitely better than the primal.
Yeah, yeah.
Okay, any more questions? If not, let's thank the speaker.
Thank you for the questions.
So yeah, thank you. And our next talk, I mean, I guess we can go ahead and start. Technically, we have another minute left, but you know, the next talk, Jan will present bipartite matching in nearly linear time on moderately dense graphs. So welcome, Jan, to the conference or to the session.
Yeah, so I'm Jan van den Brand. I'm going to talk about bipartite matching, how to solve that quickly. And this is joint work with Yintat Lee, Danupon Nanonkai, Richard Peng, Tachapon Saranurak, Aaron Sidford, Zhao Song, and Di Wang. All right. While the title here is bipartite matching, what we actually solve is something slightly more general. What we solve is transshipment. So you can think of that as something like minimum cost flow without capacities on the edges. So here we are given some directed graph, and we have some costs assigned to the edges, but no capacities. And then we also have some demands for the vertices, so how much flow a node wants to send or how much it wants to receive. And now the task is to route this flow while minimizing the cost. So a solution would be something like this here. And this captures a wide range of graph theoretic problems. So it captures maximum cardinality bipartite matching, minimum weight perfect bipartite B matching, negative weighted shortest path, and a bunch of other problems. So let's briefly look at the history here. I'm going to use n as the number of vertices and m as the number of edges. And if we look at the history of maximum cardinality bipartite matching, we see there are kind of two types of optimal algorithms. Not optimal, but two types of good algorithms. One are good if you have some dense graph as input, which is in this column, and one type of algorithm is better if you have some sparse graph as input. And we see that the exponent here decreased over and over again. And it kind of raises the question, maybe we can get something nearly linear. And we show that this is indeed possible, but it belongs to this dense column here, because this is only nearly linear time if we have at least n to the 1.5 many edges, because of this complexity here. And this algorithm also holds for transshipment, so it covers all of these other graph theoretic problems that I listed, like negative weight, shortest path, and so on. So how does this algorithm work? What's the high-level idea here? So we use an interior point method. You can think of that as some kind of reduction where you reduce the problem of transshipment to a bunch of electrical flows that you have to compute. And electric flows are known to be computable in nearly linear time. So the only thing that's kind of left is, all right, how many of these electric flows do we have to compute? And there has been a lot of research on this. The number of electric flows you have to compute decreased over time, and that's where these complexities also from the previous slide came from. Now, our approach now to attack this problem was slightly different. While everyone before tried to reduce the number of flows, we are going to reduce the time required per flow that we have to compute. So how can we reduce the time per electric flow? This interior point method, where I say we reduce to a bunch of electric flows, the idea is roughly as follows. You assume you already have some flow that satisfies the demands, and now you try to repeatedly improve the cost of this flow. So what you do is, let's say you have already a flow that is given by these black edges. You're trying to reduce the cost by repeatedly augmenting the flow by some circulation, because maybe the flow up here would be less costly. And how you compute these circulations is that you first augment by some flow that reduces the cost. But since we perform this augmentation, we are no longer satisfying the demands. So what we have to do is we have to reroute the missing amount of flow from the left back to the right. And for that, one computes an electric flow where the resistances are chosen in a good way to not increase the cost by too much. And yeah, if we perform these two augmentations together, that's exactly how we get the circulation here, which is going to reduce the cost of our flow that we want to construct here. All right, now how can we do these computations more efficiently? What we observe is that for this computation here, it suffices to do everything just in some kind of approximate way. So let's say our flow satisfies the demands only in some approximate way. So there is some small error here compared to the left. And now when we reduce the cost by augmenting by G, the demand is not satisfied at all. We try to fix this error in demand again by routing an electric flow. But since we don't have to satisfy the demand exactly, it's enough to just compute some approximate electric flow here. And since we can just compute some approximate electric flow, we can just do some, we can speed up the time that's required for this flow. Okay, so the summary here is that this interior point method reduces this transshipment problem to a bunch of electric flows. And previous research tried to reduce the number of electric flows that have to be computed. And our new idea was, let's reduce the time per electric flow by doing some approximate computations. So how do we compute these approximate electric flows? Why is this more efficient? For that, let's look at how you typically compute electric flows. So usually you're given some weighted graph as input, and you try to find an electric flow that satisfies some demand B. If you want to compute such a flow, what you do is you take the weighted Laplacian that corresponds to your input graph, and you solve this Laplacian system. Here you get vertex potentials as some vector phi. And then the flow is constructed by just taking the difference of the two endpoints for every edge and scaling the difference by the weight of your graph. And this can be typically computed quite efficiently because we know Laplacian systems can be solved in nearly linear time. And here we just take the difference of two points of the vertex potential vector for every edge that's also linear time. So this is how you usually compute an electric flow efficiently. How can we speed this up by doing approximations? So the first trick is when we have this Laplacian here, we replace that by a spectral sparsifier. So while this Laplacian here might be quite dense, it might have m non-zero entries, the new one only has n, like the number of vertices, many non-zero entries. So running the Laplacian solver on the spectral sparsifier is more efficient. The next thing is when we have to take the difference here for every single edge, that's also too slow. What we do is we sample a bunch of randomly selected edges and only compute the flow on this smaller set of edges. And that's how we get our complexity, because if in every iteration, and there are root n iterations, that was proven a while ago by Lee and Sidford, we have to solve this Laplacian system, then we get this n to the 1.5 term. And if in every iteration we sample m over root n many edges, and we have root n many of these electric flows, that's where the term m comes from in our complexity. Okay, so I said we sample random edges. How exactly do we have to sample this? What distribution is required here? So first of all, let's say f is the flow that one would usually compute. What we're doing now is, right, we compute some sparsified flow f prime by just sampling all the edges. Every edge is sampled by some probability PE, and we just scale every included edge by the inverse to make sure that in expectation, it's as if we wouldn't have sampled at all, but it's still the flow before this sampling in expectation. But just because it's the same flow in expectation doesn't mean that this sparse flow has anything really in common. So we also have to make sure that the variance is small. To decrease the variance, we make sure that our sampling probability is proportional to how large our flow is, because we scale here by the probability. Additionally, we want to satisfy this demand here, and that is given by sampling by at least the effective resistance of an edge. It's known that if you sample by at least the effective resistance, then what you get is a spectral sparsifier of the graph. And specifically for our sparsified flow, that means we're actually not just computing some electric flow, we're computing an electric flow that is on a spectral sparsifier, on a subgraph of G. And since it's just basically we're replacing this G here with a spectral sparsifier, we're really just computing the electric flow for some given demand B. So this is the given that we have the correct demand here. Okay, so the summary here is that we reduce the time required per electric flow by using a Laplacian solver on a spectral sparsifier instead of the entire Laplacian. And we subsample the flow by sampling every edge with some probability that's proportional to at least how large the flow would have been on that edge and the effective resistance of that edge. Now, if we use the sampling probability, it kind of raises a question that is, how can you even perform this sampling if it depends on the flow? Right? The point of the sampling was we don't want to compute the flow, but how can we perform the sampling without computing the flow first if the probability depends on the size of the flow? And that's covered in the full talk that's on YouTube. We create some data structure which is able to sample this when we are just given the vertex potentials instead of the entire flow. And open problems now would be our complexity is actually m plus n to the 1.5 times log squared of w, where w is kind of the largest integer that we have in the demand or cost of this flow instance. And this n to the 1.5 term is kind of bothering, right? We are nearly linear time. If we have at least n to the 1.5 edges in our graph, it would be nice to see if that can be reduced to some smaller polynomial. All right, other questions?
Yeah, we have a few minutes to take questions. So.
A question?
Question, yes?
What is the, is there hope for a deterministic algorithm with similar complexity?
Deterministic one. I don't see how, but I also don't have an argument why it should not be possible.
Can I chime in a little bit on that?
Sure.
Yeah. So one of the big reasons there's a lot of difficulty with that is that it requires generating. We need very high accuracy sparsifiers right now.
Right. So the spectral sparsifier we use has to be like 1 plus epsilon, some constant factor. It's not enough to have like a polylog approximation.
I see. Thanks.
Any more questions?
One question maybe. Yeah. Hello.
Yeah.
Okay. Yes.
Yeah. So I just curious. I mean, the n to the 1.5 term. I guess it's hard to see from the talk whether this sparsification is done upfront or it happens within. So I guess it's coming from the number of iterations and to the square root n iterations.
So the complexity currently comes from the fact that we have root n iterations. And in every iteration, we have to solve a Laplacian system with density n. There are two ways to reduce this. Would either reduce the number of iterations, or maybe it's somehow possible to create some data structure so we don't have to solve the Laplacian system from scratch in every iteration.
I guess the previous, I mean, I'm not very familiar with all this work, but how the previous work on improving max flow reduced the number of iterations, right? So I'm trying to see.
Right. So the previous work, there was something. So one issue here is that, for example, this is still scaling in the number of edges, the previous work, right, where the number of iterations was reduced. For number of iterations proportional to the number of vertices, there really exists only this result by Lee and Sidford with root n iterations.
I see. Okay. Thank you.
If there are no other questions, let's thank the speaker. Thank you. And we will move on to our next talk for the day, where Bento will be presenting Revisiting Tardus's framework for linear programming, faster exact solutions using approximate solvers. So welcome. You're muted.
Shall I begin or do we wait?
I think it's fine to begin unless there's somebody objects. So I would go ahead.
People object aren't here yet.
Yeah, I mean, I guess, yeah, you're right. We have 1 minute. Sure, I'm happy to wait. We could talk about the weather in different parts of the world for the next minute. I have a timer here that's beeping.
Okay, then.
So yeah, so now we should probably start.
Yeah, thank you. So let me again name the title. So I present joint work with Daniel Dadouche and Laszlo Feg, Revisiting Tardus Framework for Linear Programming, faster exact solutions using approximate solvers. And what we're concerned about is linear programming. We aim to minimize the linear objective over equality constraints and want that x is negative here. And famously, since the late 70s and early 80s, we have the ellipsoid method and interior point methods that solve these problems in time that is polynomial in the dimensions n and m, and the bit complexity of the problem that is L. And since then, essentially, there's an open question whether we can solve LPs also in strongly polynomial time so that we get rid of the dependency on the bit complexity L, which also is famously a Smale-Stamps question. In recent years, we had big progress regarding approximate solvers. So an epsilon approximate solution would be that we have an approximately optimal solution, an approximately feasible solution, and all that in dependence in the logarithm of 1 over epsilon. And there we have, as you see in the lower box, in the last decade, deterministic and randomized solvers depending on the sparsity of the matrix and on the relationship between m and n. And what we are concerned about in our paper is really only dependency on the constraint matrix A. So these results that you just saw, they kind of have a dependence on the right-hand side B and the objective C, but our solvers should just depend on the constraint matrix. And this has been done by Tadeusz already in the mid-80s for so-called combinatorial LP. There, if your constraint matrix is integral and you have an upper bound on the submatrices of this matrix, then LPs can be solved in time that is polynomial in m, n, and the logarithm of delta. So as you can see, we get rid of the dependence of B and C. What we are concerned about is a different condition number that is kappa. So let me quickly introduce it. If you look at your constraint matrix A and you look at the independence matroid that is formed by its columns, then we look at minimal dependent subsets. They correspond to a one-dimensional subspace of the kernel. And these elements, for them, we look at the ratio between entries of their support. And this is what we call the circuit imbalance measure. And what you can show is that, or what is straightforward, is that kappa for TU matrices would be 1. And in general, you have that if your matrix is integral, then kappa is upper bounded by delta. There's also this result by essentially Tunchel combined with our result from this year in Stock that kappa is NP hard to approximate up to even 2 to the poly n factors. Now, what is the relationship between delta and kappa? As you've seen on the previous slide, kappa is upper bounded by delta, but in the other direction, there can really be a big gap. Consider, for example, the incidence matrix of, say, a complete graph. And then what you have is that if you look at disjoint triangles, then, so importantly, we have an undirected graph. And then if you look at triangles, then they form, essentially you can pick n over 3 triangles. And then if you look at the submatrix corresponding to it, then you have a block diagonal matrix. And these blocks all have determinant 2, so you get some determinant that is 2 to the O of n. But kappa, if you think a bit about it, then you see that kappa is upper bounded by 2. So if you get logarithmic dependence on kappa, then even for this incidence matrix, you get an algorithm that is a factor n better than an algorithm that depends on delta. So going back to Tadeusz framework, where we looked at the dependence on the constraint matrix only, there are also other algorithms that depend on the constraint matrix only. Those are the layers least squared interior point method by Vavassis and Ye, which we sped up this year to a runtime that is n to the 2.5 log n log chi bar, where chi bar is some condition number that in log terms is in theta of log kappa, so they are essentially equivalent. But here we speak about linear system solves. What Tadeusz has is that she only has mn black box calls to an exact LP solver. In particular, you can plug in these fast solvers that we've seen in the previous slides from the last decade, and therefore her algorithm would be faster for those. So now the question is really, can we strengthen Tadeusz's framework so that it depends on kappa instead of delta, and that it only uses approximate solvers because these fast solvers that we saw are only approximate and not exact? And this is our contribution. So for one, we generalize Tadeusz's result to not only kappa, but also we are now able to handle real matrices A. At a crucial point, Tadeusz requires that A is integral, so we extend this result. Furthermore, we only rely on approximate solvers instead of exact solvers. And if you, for example, are interested in a deterministic algorithm, then we can plug in Van den Brand's algorithm so that our algorithm runs in mn to the omega log kappa. time. And as a third contribution, we will always certify whenever our guess of the condition number is too small. So as you've seen before, it is hard to approximate kappa. So what we do is repeatedly, we guess this condition number and increase this guess. And whenever our algorithm fails, then we know that our guess was too small, and we can point to a circuit of the kernel of the matrix, which has this high circuit imbalance measure. Okay. Now to the ideas that we use. So again, we use a black box approach like Tadeusz does. And what we rely on is proximity theory. And in particular, I will now give an example for how this works for the feasibility alone. So let's quickly switch the point of view. We looked at linear programs in form AX equals B, but we can also identify the kernel of our matrix with some space W. And then essentially what we look at is we look at some shift in the kernel of W. And you see in the lower half of this slide here that this is an equivalent formulation where we replace the matrix with just the subspace of Rn. And having this view, we have the following proximity theorem, namely, so this here is the feasibility, the prime feasibility from the previous slide. Now assume that the system is feasible, then there's also a feasible solution that is close to our vector D. And by close, we mean this is the circuit imbalance kappa times the negativity of D. And I just want to give in the short version an idea why this is, how you would prove the theorem. In the long version, I given proof. But here, just what we do is we decompose this vector x minus d that lies in W. And if you circuit decompose that, you can, you can show that that indeed this proximity theorem holds. Okay, and having that, our algorithm on a high level does the following. You initially start with some vector D that has some positive components and some negative components. And then you apply your weakly polynomial solver that decreases the negativity to some epsilon. And now at some point, if you have some small negativity, your weakly polynomial solver will never be able to solve feasibility in finite time. But what you will have with the proximity theorem is that you have the guarantee that there is some feasible solution somewhere in this confidence interval that is the orange area. And now what you do is the following. You know that for these variables here, there is a primal solution that has large values on them. So what we really need to focus on are the guys that correspond to negative variables and to small variables. So what we do is we forget about the large variables and solve recursively the problem on these small variables. And once we found the solution recursively on the small variables, we essentially lift them up to the original system. And because the variables on the variable, because the values in the variable that we forgot are so large, this lifting procedure will still keep these values positive. This is the high-level idea of what we are doing. If you execute it carefully, then you'd only need m recursions instead of n. And then this gives the total runtime of n to the omega log kappa. And this is our result for feasibility. You also have some kind of proximity theorem for optimality. Here, I just want to quickly just skip over it. So here, essentially this looks pretty similar, just to get this x additional term, and you need also an initial dual feasible solution. And then what we get is that we need mn oracle calls compared to m for feasibility, which then will lead to a total runtime of mn to the omega plus 1 times log kappa. Okay. There are still many open questions. So one would be that for primal feasibility, we have m oracle calls. For dual feasibility, we have n minus m calls to the oracle. So here the question is really, can you kind of unify that so that primal and dual feasibility would have the same hardness? Optimization currently takes mn oracle calls. If I would have had more time, then I could give more details on the optimization and why one could feel that less than mn should suffice. And then a very natural open question would be, can we extend this to systems where we have unbounded kappa? So for example, there are also proximity theorems for generalized flows, but generalized flows already have unbounded kappa. So maybe is this machinery extendable to these kind of problems? And then of course, now linear programming is essentially a conic problem where your cone is the non-negative orthant, but you still have these ax equals b constraints. So you have some affine space over which you optimize. If you change the cone, for example, to the cone of positive semi-definite matrices, or if you have the Lorentz cone, then the question could be if this whole theory would somewhat extend to these kind of problems. Thank you.
Thank you. Let's take some time for questions. Does anybody have any questions? So I hope nobody else got kicked out. Can you guys hear me?
Now, for a few seconds, you spoke without me hearing anything. Seems like she's disconnected again.
Should we take the control of the session into our own hands?
Yeah.
Okay, so maybe I should share my screen.
Okay, so Zoom kicked me out. I apologize about that. I hope, yeah, as I see, you guys made progress without me, so that's good. Good to know you don't need me. So the next speaker is Slil, and we'll talk about sub-exponential LPs can approximate max cut. So welcome, Slil.
Thanks everyone for being here. So yes, today I'll tell you about how sub-exponential linear programs can approximate max cut. And this is joint work with Sam Hopkins and Luca Trevisan. So let's begin. So broadly, the topic of this talk is a combinatorial optimization, in which we're interested in performing optimization over some discrete set, for example, max cut. So in max cut, our input is going to be a graph on n vertices with m edges, and our output is supposed to be the maximum fraction of edges cut by any partition. So for example, in this graph here on the left, the goal is to assign labels to every vertex, either plus or minus 1, such that the maximum number of edges are labeled with different labels on either end. Okay, and it turns out that computing max cut is NP hard, so we should temper our expectations for solving this problem exactly. But instead, we're interested in approximating the value of the maximum cut. So some of our best tools for optimization are linear and semi-definite programs. And in linear and semi-definite programs, the idea is the following. Our setting is that we're interested in optimizing over some complicated set. So here you can see this blue set here is complicated. And the sense in which it will be complicated is that maybe it's non-convex. For example, maybe we're optimizing over labels to the vertices of a graph, or maybe it has a large description. And the strategy will be to take our complicated set and replace it with a convex relaxation, a nicer set, possibly in higher dimensions, and optimize instead over that set. Okay, and when we do this optimization, we're over this other set, we're inherently going to get approximate solutions. So one sense in which we can get approximate solutions is we can certify a bound on the value. So if we're trying to, for example, maximize the inner product with this linear function, in the complicated set, maybe the value will be here, and in the sorry, let me use the pen. This isn't working out. So, and in the complicated set, the value will be here. So we'll get some kind of upper bound on the value of the maximization problem. And another thing that we can do is we can produce approximate solutions via rounding algorithms. So here, when we optimize over the nicer set, we'll get a solution that's not in the feasible region for the original problem, but by performing some kind of projection or rounding algorithm to the feasible region, we can get an approximate solution. Okay, so two of the most popular kinds of nice sets that we work with is linear programs, where we have linear constraints and we're working over the positive orthant. And there's also semi-definite constraints where it's the same. We have linear constraints, but we're instead optimizing over matrices in the positive semi-definite cone. And I'm not going to say too much about these things, except for that, you know, the point of this talk is to understand the quality of the approximation as a function of the relaxation size. And you can take these two classes of convex programs and you can compare them. So we want to compare the power of linear programs and semi-definite programs. And it turns out that there's a dramatic separation between the power of linear and semi-definite programs. So a theorem of Braun, Fiorina, Pukuta, and Sawyer asserts that there exists polynomial size semi-definite programming problems that require exponential size linear programs. Okay, so in general, this shows that semi-definite programs are much, much more powerful than linear programs, exponentially more powerful, in fact. And the question that I want to address in this talk is there a similarly dramatic separation for max cut and for other combinatorial optimization problems, which we know and love? Okay, so our case study will be max cut, and here is the sort of lay of the land. So for max cut, there's a trivial half approximation. You just output a random cut. It's easy to see that this will cut half of the edges on average. And seemingly the half approximation of the random cut was the best thing that we knew until Gomez and Williamson and Delorme and Polyak analyzed a basic semi-definite program, which I'll call the basic semi-definite program. So Gomez and Williamson showed that this semi-definite program gets a 0.878 approximation. And assuming the unique games conjecture, this is the best that we can do. Meanwhile, linear programs appeared stuck at a half approximation in a sort of strong sense. So combining theorems of Charikar, Makarichev, and Kothari, Mek-Energavendra, it's shown that for every epsilon, there exists some delta such that no linear program of size exponential in n to the delta can get approximation ratio better than half plus epsilon. Okay, so this seems like evidence that maybe linear programs cannot do any better than the trivial approximation, even when they have sub-exponential size. And our work is a surprising converse to the previous statement. Essentially, what we show is that if you give me a size budget for the linear program that is exponential in n to the delta, so a sub-exponential size linear program, then there exists some epsilon such that I can get a half plus epsilon approximation. So it turns out that sub-exponential linear programs do achieve non-trivial approximations to maximum cut. Okay, so this is a very surprising result in my opinion. You know, it's important to say that there's no hope that the linear programs will match the performance of the semi-definite programs. This epsilon is a very, very tiny function of delta. But sort of the important thing is that, you know, qualitatively, LPs are doing something non-trivial. And if you're the kind of person that doesn't get excited about sub-exponential time algorithms, let me say that we can also prove that linear programs can approximate max cut in graphs of bounded threshold rank. So this is a large class of graphs. Essentially, the tau threshold rank of a graph is the number of eigenvalues of the graph's random walk matrix, which are bigger than tau. And if a graph has 1 over n to the 0.05 threshold rank that is a constant, then a polynomial sized linear program can get a 0.99 approximation to the maximum cut value. Okay, so for many, many graphs, actually, LPs can give very good approximations to maximum cut. Okay, so these techniques also extend to other discrete optimization problems. For example, for unique games, we can show a similar result. So essentially, the performance of the linear program is qualitatively similar to semi-definite based programming algorithms for unique games, and we can also get many similar results for 2 CSPs. Okay, so this is the bottom line is that for many combinatorial optimization problems, we can show that linear programs give non-trivial approximations. And I sort of rushed through the history at the beginning, so now let me unfold the history a little bit more slowly and convince you that this is a surprising result. Okay, so in 1995, Gomez and Williamson showed that the semi-definite program can get a non-trivial approximation for max cut. And in parallel, there was a line of research that showed very strong lower bounds against linear programs. And most of these lower bounds are lower bounds against what's called linear programming hierarchies. So for example, I'll talk about the Shirali-Adams hierarchy here, but this general picture applies to all hierarchies. Essentially what an LP hierarchy is you start with a basic linear programming relaxation, and then the hierarchy gives you a way to systematically strengthen the basic linear programming relaxation until you arrive at a very large but very powerful linear programming relaxation. So if your original LP relaxation had n variables, then the second level of the hierarchy will have n squared variables, the third level will have n cubed variables, etc. And the exponential sized programs give you integral solutions. So in general, the level D relaxation has size n to the d. So in 2006, Schoenbeck, Tulsiani, and Trevisan showed actually exponential lower bounds for linear programs in the Lovász-Shriver LP hierarchy. So this is a different hierarchy, but exponential lower bounds. seemingly showing a exponential separation between linear programs and semi-definite programs for maxcut. And in 2007, De La Vega and Mathieu showed that polynomial-sized Shirali-Adams linear programs, so basically linear programs in the Shirali-Adams hierarchy down here, can't get approximation better than 0.51. In 2009, Charkar, Makarchev, and Makarchev strengthened this significantly to show that sub-exponential-sized linear programs in the Shirali-Adams family can't approximate better than 0.51. And okay, this might just convince you that the Shirali-Adams isn't very good, but it actually turns out that in a concrete sense, Shirali-Adams is the most powerful linear program. So in 2012, Chan, Lieger, Ergvenner, and Sawyer showed that if any linear program of size n to the d can get ratio rho, then the Shirali-Adams LP of size n to the 2d can also get approximation ratio rho for any d constant. And then this result was extended to LPs of any size by Kothari, Mecca, and Rikovenka. So altogether, it looks like Shirali-Adams LP of sub-exponential size can't get approximation ratios better than 0.51. And also this implies that no LP can get of size, sub-exponential can get approximation ratio better than 0.51. So things are looking very bad for linear programs. And then in just last year, in a paper with Ryan O'Donnell, we showed that in pseudo-random graphs, essentially graphs that are expanders, polynomial-sized Shirali-Adams LPs can get ratio close to 1. So this, I won't try to unpack this technical statement. But the question is, how do you take this result and extend it to arbitrary graphs? Okay, and essentially that's what we did. So I don't have that much time to talk about why, but one of the challenges is that in this paper with Ryan, we required that the eigenvalues, every eigenvalue be bounded in magnitude. So it's not just expansion on one side, but expansion on both sides. But in graphs that have large maximum cuts, there's always an eigenvalue of large magnitude close to -1. Okay, so in this work, we build on the ideas of O'Donnell, Schramm 19, and we get an algorithm that performs rounding in low threshold rank graphs. And then we use graph partitioning ideas similar to the ones used in Rohrer, Bruck, and Steuer, and in Steuer's works for unique games to partition the graph into pieces of low threshold rank and solve the problem individually on each piece. And at the core, there's this interesting, in this way we get a result that says that sub-exponential size LPs can give non-trivial performance for max cut on any graph, which is a pretty surprising result. And this is a converse to this lower bound. So the lower bound says that no LP of size 2 to the n to the 0.01 can get approximation better than 0.51. But we show that an LP of size 2 to the n to the 0.01 approximates max cut by at least half plus a pretty small constant that doesn't depend on n. Okay, so I guess I'm pretty much out of time. I'll just mention one open question. So Gomez-Williamson rounding gives more refined guarantees for approximation. So in graphs where the max cut value is very close to 1, they can get a rounding that is better. And in our work, our techniques completely preclude this. The question is, can linear programs achieve similar approximations, or is there still some qualitative separation between LPs and STPs? Okay, so that's it. Thanks.
We have 1.5 minutes for questions. I actually have a question, unless someone else has. Are those techniques like specific to max cut, or like if I say independent set or some other problem? You know, of course, the parameters, the constants, you know, all of this will be different. But something like that, any of the techniques?
For independent set, believe that it should be okay. Yeah, I think independent set will work. Yeah, the sort of the issue is the partitioning step. So
yes.
Yeah, but because an independent set, yeah, I think it should be okay.
So I mean, basically anything other than unique games where you can throw away edges in the partitioning, or like unique game style,
Yeah.
I guess.
Right.
That part would be the sticky point to generalize, like the partitioning low threshold. Yeah.
That's right. It's all about whether you can throw away the edges that appear in the partition. The result for pseudorandom, for the pseudorandom setting where you have the bounded eigenvalues, I mean, yeah, the low threshold rank setting, it should work for any Boolean optimization problem, I think.
Yeah. I'm talking about general, sub-exponential time. Yeah. Okay, thank you. We're out of time, but if you do have a quick question, I mean, I guess we can be a minute late or something. Otherwise, we can thank the speaker. Okay, so let's thank the speaker. And the next talk is by Chris Jones. He's going to talk about sum of squares lower bounds for Kirkpatrick model via planted affine planes.
Okay, thanks for the introduction. So yeah, this talk is about lower bounds instead of the power of convex relaxations, and specifically lower bounds for sum of squares. And this is joint work with Moreno Conti-Ghosh, Fernando Granja-Geronimo, Aaron Petechin, and Gautam Rajendran. And I should say that Fernando is currently on the postdoc market, so feel free to reach out. Okay, so what's the problem we're considering? The problem is the so-called Sherrington-Kirkpatrick problem. It's an average case problem where the input is a matrix W in n dimensions. And the goal is to maximize the quadratic form X transpose WX over the Boolean hypercube. And here the distribution of W is the Gaussian orthogonal ensemble, or GOE, which is a symmetric matrix with normal entries. So this problem's been pretty well studied. And in computer science, you might think of it as a max cut on the complete graph, where the edge weights are random Gaussians. And it's also been studied in statistical physics, where they view it as you're trying to minimize the energy of some physical system, and W encodes the interaction strength between the particles of the system. Okay, so what's known about this average case problem? Let's define the notation opt of W to be the maximum over the hypercube of the quadratic form. Then it's evident that the optimum of W is always less than or equal to this 2 times n to the 1.5 factor with high probability. And this is just because the maximum of the quadratic form over the hypercube is bounded by the maximum eigenvalue of W times n. And that eigenvalue follows the Wigner semicircle law, which gives a factor of 2 times n to the 1.5. But the true optimum turns out to be significantly smaller than this. This is a famous conjecture from physics by Parisi from 1979, which was finally proved by Talleyrand in 2006. It says that the true optimum value is approximately equal to 1.52 times n to the 1.5. And it's here, this constant is known as the Parisi constant, P star. So something significantly smaller than 2. But these results are non-algorithmic. So as computer scientists, we might ask what kind of algorithmic progress can be made on this problem. So one thing you might consider is the optimization problem, in which you're given this matrix and you need to output an X. And actually, this problem was incredibly solved by Montanari in the last year or two, subject to a statistical physics conjecture that the model is so-called full RSB. So Montanari gave an algorithm which runs in polynomial time and outputs an X, which satisfies the quadratic form is at least 2 p star minus epsilon times n to the 1.5. So we're concerned with kind of a different problem, the certification problem. So in the certification problem, what you have to do is you have to output an upper bound on the maximum of on the objective function value that is supposed to get close to the true optimum value. So it's kind of dual to the optimization problem. In the optimization problem, you're kind of lower bounding the objective function value by exhibiting an X with a large value. In the certification problem, you have to upper bound the objective function value by outputting an upper bound on it. So you might be wondering, why can't you always just output 2 p star plus epsilon? Well, your upper bound always has to be feasible. It always has to be an actual upper bound on the objective function value. And even though that 2p star plus epsilon holds with high probability, it doesn't hold all the time. So you can't always output that. So for example, this eigenvalue, the maximum eigenvalue of W is an upper bound that you could output, which achieves value 2, which is not close to the Parisi constant. So one standard approach for the certification method is to use the sum of squares algorithm. So sum of squares is very general. It works whenever you have a polynomial objective function and polynomial constraints. And kind of as was mentioned in the last talk, it's parameterized by this degree D, with large degree is more powerful SOS. And the question that we're interested in studying is how good is SOS at certifying the shared chain Kirkpatrick problem? So in some previous works built up to this degree 6 lower bound for SOS, and they showed that the degree 6 bound is not very good. It doesn't certify anything better than the eigenvalue certification. And what we show in this work is something a lot stronger. We show that even degree n to the delta for some constant delta SOS still has the same value as the eigenvalue certification, and this holds with high probability. So in particular, this rules out any constant degree SOS for certifying anything better than the trivial eigenvalue. So what's the method we use? We go through this other problem called planted affine planes, which I just want to define for you quickly. So in the planted affine planes problem, it takes place in dimension n, and there are m random Gaussian vectors. And it's a feasibility question. You need to check whether or not there's a vector v whose squared inner product with each of the random vectors is equal to 1. So in geometrically, this you're checking whether or not this vector lies in the intersection of a bunch of parallel planes to the input vectors du. So what we prove is SOS is not very good at refuting this problem. And for m, in fact, up to n to the 1.5, it still thinks this system of equations is feasible, even though in fact, even for m, some constant times n, this system is not feasible with high probability. So the remainder of the talk is going to be the SOS lower bound for PAP. It's not really important to remember the details for the PAP problem. And using some work from one of the previous papers, MRX, we're able to reduce the Sherrington-Kirkpatrick problem to the PAP problem. Okay, so how do you prove a lower bound for this PAP problem? At a high level, we kind of follow this generic recipe for proving SOS lower bounds from this paper by Barak, Hopkins, Kellner, Kathari, Moitra, Petechin for planted clique. So to construct an SOS lower bound, it's a convex program, so you need to construct a dual object to show a lower bound. The dual object for SOS is a so-called pseudo distribution, which is specified by pseudo moments. An equivalent way you can specify this pseudo distribution is by constructing a moment matrix M. So the entries of the moment matrix are the pseudo moments of the pseudo distribution. And it's a block matrix with different blocks depending on the degree of the moment. And what we need to show to construct this dual object is we need this M to satisfy some linear constraints on its entries. And it also needs to be PSD. Okay, so the recipe for constructing M following this planted clique work is 2 steps. First, you construct a candidate moment matrix using the pseudo calibration technique, gives you the matrix M. Then you need to prove, and it's guaranteed to satisfy the linear constraints at that step. Then you need to prove that this matrix is PSD. And the way that paper does it, and that we do too, is we decompose the moment matrix into graph matrices, which are like smaller component matrices, and then use some careful study of the decomposition to prove the moment matrix is PSD. So now I'll give some of the kind of more technical details on how to do those 2 steps for the recipe for this particular problem. Okay, so here's the graph matrix decomposition. You don't really have to understand this formula, but using pseudo calibration, the pseudo calibration technique, without too much work, you can get this decomposition. So the moment matrix is a sum over some shapes, beta, of some coefficients times these graph matrices, which I'll denote M beta. So just to give you a little bit of intuition for what this decomposition looks like, the moment matrix looks like this, and the graph matrices live in the different blocks of this moment matrix. So each of these graph matrices is specified by one of these graphs, multigraphs, with labeled edges. And it corresponds to some matrix that lives in that block and is 0 on the remaining blocks, and they come with some coefficients. So the graph matrices also have these like left and right sets, which are this blue and red set. If those two sets overlap, then those are the purple colored vertices. And the vertices also come in two different types, squares and circles. So this is the graph matrix decomposition that you get just by applying pseudo-calibration. One of the key facts about graph matrices that like makes them useful to work with is that their norms are very easy to, well, not easy, but they can be understood. You don't have to read this theorem statement, but what it says is that the norm of any m sub beta is determined by some combinatorial properties of the graph beta. So just by looking at the shape, you can estimate the norm of a graph matrix. Okay, so we have this decomposition. How might we use it to prove that M is PSD? Here's a naive first idea. Some of the shapes contribute an identity matrix along the diagonal of M. We might show that all the remaining shapes have little o of 1 total norm. That would actually show that the matrix has all eigenvalues within 1 plus minus little o of 1, so it's clearly PSD. Okay, this actually works for some shapes that appear in the decomposition. For example, using the graph matrix norm bounds on the previous slide, you can just show that this term contributes little o of 1. But other shapes that appear in the decomposition do not have little o of 1 norm, unfortunately. So let's try and understand what the shapes are that appear in the decomposition, which have large norms. Towards understanding them, we make the following definition. A spider is a shape which has two squares, which are degree 1 and are adjacent to the same circle. And they must appear in either the left blue side or the right red side. So for example, these are a couple different samples of spider shapes. And then what we show is that actually, if you look at the contributions to the moment matrix of all the non-spider shapes, it has a little o of 1 contribution. So therefore, really the only shapes you need to worry about are these large norm spider shapes. Okay, so how do we deal with the spiders? Well, here's a trivial observation. It suffices to prove that the moment matrix M is PSD on the complement of its null space. Okay, well, it turns out that the spiders actually have approximately 0 action on the complement of the null space. This is actually a somewhat incredible fact, that these large norm shapes just happen to be approximately 0 on the complement null space. And on the rest of the slide, I want to kind of give a picture demonstration of why this is the case. First of all, why does the moment matrix actually even have a null space? Well, it turns out that the null space is induced by the constraints of the PAP problem. That is, if you just look at the constraints, any moment matrix which satisfies those constraints necessarily has a null space. In fact, this product that I've written on the screen here is essentially equivalent to the fact that M satisfies the constraints of the PAP problem, that M times this particular graph matrix is equal to the 0 matrix. So it has this null space, and these are the null vectors that appear in the null space. So a spider, such as the one here, it can be approximately factored so that the null vectors appear in the spider, as on the right side of this screen here. And because of that factorization, because those null vectors appear in the spider, that implies that the spider has 0 action on the complement of the null space. Okay, so that's a very high level picture, but the theorem we're able to prove is that there is some matrix M prime whose it's equivalent to, it has the same quadratic form value as M, as long as you look at the complement of the null space. And by the virtue of the fact that we've gotten rid of all the spiders from M prime, it has all eigenvalues concentrated within 1 plus minus a little of 1. Okay, so that's the high level overview, and that's really all I wanted to say. There's a couple open problems left over from that. I guess besides understanding that kind of amazing fact that just by looking at the constraints, we could understand the large norm terms in the graph matrix decomposition. There's also some other open problems. So one is to interpret Montanari's algorithm as rounding SOS, possibly. I guess if you want to ask more about these open problems, then feel free to ask questions since I'm kind of out of time. Thank you.
So let's we have like a minute or so for some questions, if you guys have some.
Question. Do you Do you have a conjecture of how the value should change as you get into the linear in N regime?
I read in some paper that it's conjectured that n over log n still cannot certify anything better than 2 minus the low of 1. So I guess linear in n might be able to do it.
Thanks.
Do we have any more questions?
Yeah, I guess to follow up on that one too, the techniques in this paper seem pretty difficult to extend to something that high, a degree that high.
Okay, let's thank the speaker. Thank you. And we will move on to the last talk of this session. And Sharat will give us, we'll talk about approximation algorithm for stochastic minimum norm combinatorial optimization.
Thank you, Alexandra. I'm just going to do some testing. Is my voice audible?
Mm-hmm.
And it's a slight transition. Okay. Do you see the introduction slide now?
I do, yes.
Okay, great. Thanks. Hello, everyone. I'm Sharat Ibrahimpour. Welcome to this talk on approximation algorithms for stochastic minimum norm load balance combinatorial optimization. This is joint work with my advisor, Chaitanya Swami. This work is motivated by growing interest in optimization under uncertainty, where many of the problems fall in the below setup. We have costs that are described by random variables, and we need to take decisions while knowing only distributional information of these costs. This is sometimes called one-state stochastic optimization. Each feasible solution induces a random multidimensional cost vector. Let me mention two concrete problems to elaborate on this point. In stochastic load balancing, we have a set of n stochastic jobs that are to be processed on exactly one of m unrelated parallel machines. The processing time of a job j on machine I is a random variable that is denoted by xij. An assignment of jobs to machines induces a random load vector on the machines. The load on a machine is simply the sum of job random variables that are assigned to it. The second problem that we consider comes from spanning trees. Here we have an undirected graph on n vertices with stochastic weights on the edges. Feasible solutions to this problem are given by spanning trees. For the tree highlighted in red, I've shown the induced cost vector, which consists of the edge variables that participate in the tree. Observe that I haven't yet described the objective in these problems. Let's go back to the introduction slide. We measured the quality of a solution by aggregating entries of the induced cost vector in a certain fashion. And our goal in such problems is to find a solution which has good objective value in expectation. The most commonly studied objectives are min-sum and min-max objectives. Minimizing the sum of cost models utilitarian view, whereas minimizing the maximum cost models egalitarian view. In the context of spanning trees, minimizing the sum of cost leads to the well-known minimum spanning tree problem, and minimizing the maximum cost leads to the bottleneck spanning tree problem. For load balancing, minimizing the maximum machine load is a classical problem. It is often called mixed-span minimization in scheduling literature. Min-max and min-sum objectives have the tendency to skew solutions in different directions. So LP norms can be helpful in modeling a mix of these extremes. Since objective functions are a means to an end, it is natural to ask if we can design algorithms that can work for a wide class of objective functions. To this end, Chakrabarti and Swami considered the class of monotone symmetric norms and gave constant factor approximation algorithms for load balancing and clustering problems arising from such objectives. Let me formalize what I mean by a monotone symmetric norm. A norm is monotone if increasing a coordinate does not lead to a decrease in the norm. and the norm is symmetric if it is invariant under permutation of coordinates. In this talk, I'll often use the notation x with a superscript of down arrow. This is shorthand for the vector x with its coordinates sorted in non-increasing order. Let me mention two benefits of working with the class of monotone symmetric norms. The first benefit is that we can capture a lot of interesting objectives under one umbrella. For instance, all LP norms are in this family. There's another subfamily of special norms called top L norms, which are building blocks of all monotone symmetric norms. The top L norm of a vector is the sum of its L largest entries. Top L norms give another natural way of interpolating between the min-max and min-sum objectives. The second benefit comes from the observation that a point-wise maximum of monotone symmetric norms is yet another monotone symmetric norm. So an optimization problem with multiple norm budget constraints can be cast as a minimization problem with a single norm objective. I'll now give full descriptions of the two problems that I mentioned earlier. In stochastic load balancing, we'll assume that the job random variables are independent, but there can be arbitrary correlations among the machines. We also assume access to complete distributional information of the joint distribution of variables corresponding to job J. Since jobs are independent, the machine loads are independent random variables. Our goal in this problem is to find an assignment of jobs to machines that minimizes the expected F norm of the induced load vector. Here, F is a monotone symmetric norm that is given as part of input via a value oracle, say. I'd like to repeat that the assignment that we find should be oblivious to the actual job size realizations. For the problem on spanning trees, we assume that the edge weight variables are independent and that we are given a monotone symmetric norm F. Our goal is to find a fixed spanning tree that minimizes the expected F norm of the induced cost vector. More generally, we motivate the abstract problem of stochastic minimum norm optimization, where we have an underlying combinatorial optimization problem. We assume that the coordinates of any induced cost vector are independent. Our goal is to find a feasible solution that minimizes the expected F norm of the induced cost vector. Our contribution in this work is to develop tools and techniques to reason about the expected norm of a random vector whose coordinates are independent random variables. For convenience, we shall refer to such a random vector as a product distribution. Observe that we can lower bound the expected norm by the norm of the expected sorted vector. Note that before exchanging the expectation and the norm, we sorted the cost vector. Symmetry of F is used in the equality and convexity of norms is used in the inequality. Surprisingly, in the case of monotone symmetric norms, this lower bound is quite strong. This result forms the backbone of our work. Let F be an arbitrary monotone symmetric norm and capital Y and capital W be product distributions. Our main mathematical theorem says that the expected norm of a random vector is within a constant factor of the norm of its expected sorted vector. Let me mention how our main theorem gives us a framework for stochastic minimum norm optimization. I want you to view W as the cost vector of an F optimal solution and Y as the cost vector of a solution that we want to compute. An immediate consequence of our main theorem is something that we call approximate stochastic majorization. If for all L, the expected top L norm of Y is bounded by alpha times the expected top L norm of W, then we can infer that the expected F norm of Y is bounded by order alpha times the expected F norm of W. This result is a substantial generalization of the majorization inequality in the deterministic setting. Anyway, so the main takeaway from this slide is that at a constant factor loss in approximation, we have a reduction from stochastic F norm optimization to simultaneous stochastic top L norm optimization over those L's that are powers of 2. Due to time constraints, I'll only go over high-level applications of our framework to designing approximation algorithms for stochastic load balancing and stochastic spanning trees. All our algorithms are LP-based and use iterative rounding. Our first application is an order 1 approximation for stochastic minimum norm load spanning tree with arbitrary edge weight distributions. This theorem also generalizes to the matroidal setting. Second, we consider stochastic load balancing. We start with the special case when the objective is a top L norm. Here, we give an order 1 approximation when job sizes are arbitrarily distributed. This theorem generalizes Gupta et al.'s work on minimizing the expected make span. Next, for stochastic load balancing with Bernoulli jobs, we give an order 1 approximation for arbitrary monotone symmetric norm objectives. This result can be viewed as the simplest stochastic generalization of Chakrabarty and Swami's work on deterministic minimum norm load balancing. Lastly, when job sizes are arbitrary, we give a simple yet non-trivial order log m over log m approximation based on Chernoff bounds. Over the next 2 slides, I'll sketch a proof of our main theorem, which states that the expected norm of a random product distribution is within order 1 of the norm of its expected sorted vector. Let the random variable n denote the number of coordinates in y that exceed a threshold theta. The blue curve shown below is a plot of the expected value of n against theta. This curve is simply the sum of upper cumulative distribution functions of the coordinates of y. For convenience, we refer to this curve as the expected histogram curve. Of special interest to us are thresholds tau L, where the height of the blue curve is L. I've also marked thresholds tau 1 and tau 2. Let gamma 1 denote the area of the dotted region. Let me elaborate on why these quantities are important to us. It turns out that the F norm of the expected sorted vector, which is on the right-hand side of the title of this slide, this F norm of the expected sorted vector is within a constant factor from the F norm of the vector with entries gamma 1, tau 2, tau 3, and so on. For convenience, we'll refer to this vector as the blue signature, okay, because it's a signature of the blue curve. We are now ready to finish the proof of our main theorem. We just need to relate the expected norm of y, of a random vector y, to the norm of the blue signature. First of all, observe that the number of large coordinates in y with respect to threshold tau L is a sum of independent Boolean random variables, and the expectation of this number is at most L. By Chernoff bounds, the number of large coordinates with respect to threshold tau L strongly concentrates around L. Here's what we are going to do. We sample a vector little y from the product distribution of capital Y, and then overlay its histogram curve on the expected histogram curve of capital Y. For deterministic vectors, the signature is simply the sorted vector. We call the signature of little y as the green signature because I've shown the histogram in green. Here's the crux of our proof. The probability that the green curve lies below alpha times the blue curve rapidly approaches 1 as alpha grows. Since the norm is monotone, the expected norm of capital Y is within a constant factor of the norm of the blue signature, which finishes the proof. I'll conclude this talk with the following 2 open questions. The most pressing question is whether there is an order 1 approximation for stochastic minimum norm load balancing with arbitrary job size distributions. This is open even in the identical machine setting. The second question is purely mathematical. What's the best upper bound on the expected norm of a random vector in terms of the norm of its expected sorted vector? In the full version of our paper, we showed a bound of 28. We have been able to bring it down to 12, but we believe that the true gap is much smaller. Thank you for coming to this talk.
Thank you. We have a few minutes, a couple of minutes, I guess, to take some questions before the session ends.
I have a question for Sharad. So
sure.
Is there some sort of a complete characterization if the expected f of y is within constant factor of f of the expectation, where f is a norm, then f has to be some sort of monotone symmetric norm? Is that?
Like so far we don't have any, but the way the bound is written, the lower bound, like symmetry is used to obtain the lower bound. Maybe if it's not symmetric, then we haven't really thought about this like a full characterization. So right now I don't have like an answer. Yeah. That's a good question. Like to have like how far can we extend? Like what I see is that maybe for more general convex functions, like we can give like based on like how fast the curvature grows, maybe we can like give weaker bounds.
I mean, is it could it be some polylog for some weaker functions or such? That's what I was
saying. There is definitely like a possibility of such kind of results. Like if we know that like increasing the coordinates by factor 2 for norms, like the norm grows by factor 2, but let's just say if it only grows by like a factor 4, 2 squared, then our results imply like such a corresponding result, like a slightly weaker result, but it still gives reasonable results.
Thank you.
You're welcome.
We are technically out of time, but since this is the last talk of the session, if we have another question, we can take it. Otherwise, let's thank the speaker. And thank you everybody for a wonderful session. I will see you again in the next one.